No.
Hey guys, welcome back. Matt Young here with Flowco, and welcome to Series 4 Production Optimization. So today we have Robert Strong with us to help us as a guest host to talk through this application here, primarily getting into optimization, utilizing nodal analysis to really pick, tubular sizes, things like that. So welcome. Thanks, Robert.
Yeah, glad to finally be in front of the camera. I'm usually back there making sure everything's running right.
That's right. Yep. Robert's usually our behind the scenes guy, making sure you guys can hear us and see us and everything flows right. So, how does it feel to be on this side of the camera?
It's a little weird.
Would you prefer to be back over there?
Maybe.
Okay. Well, we'll only keep you for this episode then. How about that? So, man, another thing coming up. You ready for your big day, your wedding this weekend?
As ready as I can be.
Yeah, not too nervous?
A little bit.
All right. Can we live stream that and make it Series 5?
No.
Robert's wedding?
No.
Okay. Non-technical?
No non-technical presentation.
I got you. We'll just stick to the technical presentations then. But anyways, guys, thanks for joining. A couple things before we dive into the presentation. Mainly want to go over kind of just an overview of what we'll talk about so they guys can see this on the TV behind us. But so today is production optimization. We should have a couple bullet points on the screen. Robert, if you want to move to the next slide that shows, yeah, there we go. So really want to talk about production optimization through the use of nodal analysis, building VLP curves, or those vertical lift performance curves, understanding the deliverability through IPR or a PI line, and really what we look at from a production standpoint is how that can help us through artificial lift selection. It can be what artificial lift we select, what tubular size we put, our ideal wellhead pressure, maybe what into tubing placement, or heck, even flow path. Do we do casing flow or tubing flow or annular flow?
Yeah.
So those are things we really want to talk about today. Especially with these unconventional resource plays where a lot of times we see these wells IPing up casing, right? Their initial productions produced up casing. Well, we know that's not long term, right? So what do we do after that fact?
Well, I mean, we everyone wants to know what's going to happen when you install tubing.
Exactly.
And nodal analysis is a really good way to evaluate, what's going to happen once you do put that in there. So yeah.
So that's what we want to look at today is, yeah, exactly. Just like Robert mentioned, what's going to happen if we do this? If we do this, how's that going to change our production gradient? How's that going to change our flow and bottom hole pressure? And of course, how's that going to affect our production, positive or negative? So it's a very useful tool. And really, in my opinion, for any artificial lift company, any production engineer, and any operations person, they should have access to some kind of production enhancement optimization software to be able to go through and run those cases. And so in today's presentation, we'll be able to kind of show some of those steps and different ways we can use it. So good. Well, and one other thing before we get started is we will record this video. When we get done today, we'll post that up on Flowco website. So if you guys missed it, if you had anybody that wasn't able to attend, they can always go back and watch that as well. With that, you ready to get started, Robert?
I'm ready.
All right. Okay, so guys, we're on Series 4 this year, another technical presentation, primarily focused on production optimization, utilizing a nodal analysis software. And so really the objective of, one, this presentation, but two, why we want to use some kind of nodal program for production optimization is we want to look at both the inflow, what the well is capable of delivering, as well as the outflow. How do we handle that production out of the well? And we ultimately want to match those two up, right?
Well, yeah, the inflow, we're going to be matching the production of the well, and the outflow is the only thing that we can really control.
True. Yeah, good point.
So
And with that outflow, like Robert mentioned, there's multiple ways to match it up. If we have things like a downhole gauge or maybe an ESP on the well where we can actually collect that flowing bottom hole pressure, we can do like a 1 or 2 production test Vogel IPR curve. If we have reservoir pressure, then we can build onto that as well. So we'll point out some of the different ways to build that inflow calculation. But like Robert mentioned, primarily we want to focus on the outflow because those are the things that as a vendor or as operations group or as an engineer, those are the things that we can control, right?
Yeah. And we're in the artificial lift business, so that's what we're looking at.
Exactly.
Yeah, that curve is
we,
pretty as possible.
We live and die by those outflow curves, right? And so a couple things just for anybody that's new to it, we'll call it an outflow curve, we'll call it a multi-phase flowing gradient, we'll call it a VLP curve. They're all essentially the same thing, right? It's just the wonderful world of the oil field where one thing is named 5 different ways.
Vertical lift performance. I like that.
You like that one?
Yeah.
Okay. We'll try to stick with that today then. But one of the pieces that we look at from the VLP, that vertical lift performance curve, is it's a mix of a couple things, right? Ultimately, it is your flow diameter from into tubing or perforations up to surface. Let me grab my pointer here so we can show it a little better. But additional things that kind of compound or add to that VLP curve, right, is what's our wellhead pressure? And more importantly, what's that pressure drop between our wellhead and our separator, typically controlled by that flow line diameter and length. And so we'll like to look at our surface piece that affects the VLP curve, and of course our VLP curve based off of that flow area, PVT properties, production rates, things like that. And ultimately, we're trying to match this flow and bottom hole pressure with our inflow to, ultimately get the best production out of the well we can. And one thing we'll talk about here in a few slides is dimensional IPR curve. So
yeah, we have a lot of good slides to show you in terms of sensitivities for all this stuff. So if you stick around towards the end, you'll be able to see kind of how your wellhead pressure will affect things, tubing size, injection rates. We'll get into everything. So
yeah, definitely. Yeah. So but before we get started with that, Robert, we got a nice little video here. You borrowed this video from Neil over at Zytec. In my opinion, I think he does a really good job of just kind of summarizing what we're going to talk about today between that inflow and outflow. So we'll go ahead and play this quick video for you guys, and then we'll get back into some of the presentation content. Let's see.
Into the reservoir and considering an imaginary point at reservoir depth. This point will have a certain ambient pressure, known, unsurprisingly, as a reservoir pressure, or sometimes shut-in bottom hole pressure. The first concept I'd like to introduce is reservoir productivity, or more specifically, productivity index, measured in barrels per day per PSI. This is how it works. If we draw down, that is, lower the pressure at our imaginary point, then fluids will flow to that point at a specific rate. We then have a flowing bottom hole pressure at that point. If we draw down more, the flow rate will be higher. Simple. But the great thing about this is that all the relevant reservoir and fluid properties are built into this single line. The PVT properties of the fluids, the temperature, the porosity, permeability, height, net to gross, and the skin, which is the amount of damage the drillers do when they drill the well. So we have here a very simple but a very powerful tool. I guess I should admit to oversimplifying things just a bit, because when the ambient pressure is reduced to below the so-called bubble point pressure of the fluid, then liquids and gases separate and they have their own lines. A chap called Vogel had a lot to say about this back in the 60s, I think it was. But anyway, I think you get the message. So now let's complete the well and move on to outflow. Referring to the same imaginary point, a certain flowing bottom hole pressure is required to drive the fluids to surface. This is called the outflow performance of the well system. At low pressures and rates, the fluids tend to misbehave, but otherwise, what we see here is another very simple relationship. A certain flowing bottom hole pressure will drive fluids to surface at a certain rate. Higher flowing bottom hole pressure, higher rate. Simple. But the really cool thing here is that all relevant wellbore and fluid properties are built into this line. Again, the PVT properties of the fluid, the temperature profile, conduit properties, and tubing head pressure are all considered. Again, we have a very simple but a very powerful tool. So let's summarize. We have inflow and outflow relationships. Both refer to the same point in the well, and both are plotted on the same type of graph. That means we can cross-plot to see how much our total well system will produce. Brilliant! All things considered, our well will produce at this flow rate. Sadly, however, this is not always the case. Sometimes when we cross-plot, the lines don't cross, and so there's no unique solution and no flow. This is a dead well, and I think you all know where we're going now. This illustrates the fundamental need for artificial lift. But before we think about artificial lift, let's talk about other ways that we can make this well flow. Firstly, we can lift the inflow performance line. What we're doing here is increasing the bottom hole pressure without changing the gradient of the line, which is the productivity index. We make the lines cross.
So one thing we like about that video, Neil does a good job of just kind of illustrating those points and that kind of matching of both that inflow and outflow piece. So, one of the few things we want to talk about is both that performance from the inflow side, what's the well capable of producing, and then secondary to that outflow piece. That's the big piece that we can control, right? We can control that vertical system through tubing size into tubing placement. And then we can also control some of the horizontal systems too. How long is that flow line to the separator? What's our separator pressure going to be at? What's the diameter of that flow line as well? So really, and this is where it becomes important, right, is bridging those two pieces together, bridging that inflow performance either off of maybe a target rate, if it's a new well that we haven't completed yet, or if it is a producing well, grabbing those well tests plus that bottom hole pressure to really build out that deliverability curve. And then once we have expectation for that deliverability curve, then we can match that VLP curve together with it, right? And again, like Robert mentioned, this is the big piece that we can control when we're ready to produce that well.
Yeah, lots of people like to look at things theoretically. They want to know what it's going to produce in the future and what we should optimize for ahead of time. But then you end up coming back and actually matching your production data and plotting everything to it.
Yeah,
so.
Yeah, you're exactly right. And that's important. And one thing to note about that comment too, Robert, is we're primarily going to talk, and I'll go to the next slide that kind of illustrates that. We're primarily going to talk about what would you call that? Like a high bubble point pressure, unconventional well, which means we're going to be following more of a Vogel type IPR curve. And so two, in my opinion, with these unconventionals is this IPR curve is ever changing, right? It's always working its way to the left, either through a reduction in reservoir pressure or permeability, or sometimes both, right?
Yeah.
And so it's important that when we are making these deliverability curves, that we need to update them when we get new tests, new bottom hole pressures, things like that.
Yeah.
So, and this little graph here kind of represents the difference between a PI productivity index and our inflow performance relationship, that IPR curve. And they tend to follow in a similar linear path until you hit that bubble point. And just kind of my opinion, it seems like most of the time when we're looking at something like artificial lift, we're already past that bubble point pressure. So we're already kind of on that deviation away from that PI. So things to look at. Typically, we're going to deal with that IPR curve, right?
Yeah.
So, and again, like we said, two methods here, PI, IPR. Usually when we're considering things like tubing, artificial lift, we're already past that bubble point in most cases. So we typically focus on that IPR, at least from like your unconventional standpoint. So again, so like to talk about that inflow piece. Again, like Robert mentioned, we can't really control that. But what we can control is that outflow side. And so understanding what our handling capabilities are against that production rate is important. And then picking the right systems in place to do that. And that could be, and you'll see examples of this, but that could be what? Tubing size, flow path, wellhead pressure through like flow line size. Maybe we need to upsize our flow lines if we're flowing back to a centralized tank battery, things like that. And then, of course, picking the right gradients as well. It looks like we have a question. What's that, Jennifer? Okay.
Yeah, unfortunately, the meeting settings didn't take. So if you wouldn't mind just muting yourselves.
Okay. Yeah. So one of the things, again, from that outflow side, we want to look at how low can we get our separator pressure, right? Our separator pressure along with our flow line will back up and either benefit or hinder us on that flowing wellhead pressure. And of course, there's other things we can do from like removing chokes or any kind of directional change on our wellhead. Other things that can affect that VLP curve are going to be like deviation, of course, which we see with these unconventionals, especially multi-pad type directional drilled wells. Water cut's a big one. And of course, just the general physical properties of the fluids that we're producing. If we're producing heavier water, higher water cut, our friction's going to take over. We're going to have more pressure loss from that, which will lead to a higher flowing bottom hole pressure. And of course, that coupled with tubing size can really compound those frictional pressure losses.
And people are more and more interested every day in seeing correlations that can use the deviation in those. So GUO, I think we're starting to look at, and some people are coming up with ways to use GUO to actually do a hydraulic correlation.
Oh yeah, that's a good point. And let's jump ahead while you're talking about that, Robert. So when we talk about those multi-phase flow correlations, here's just a couple reference. But yeah, you bring up a good point, is that a lot of these, especially the empirical models, don't typically take deviation into effect, or it's not a big factor in terms of that.
I would say almost none of them have any sort of deviation built into them.
Yeah.
So yeah, that's kind of where the bleeding edge is right now in terms of trying to model this stuff. But we stick to Hagedorn and Brown for our high liquid rate stuff. Duns and Ross is going to be your good one if you have a gassier well. It's usually good for like lower production. You're talking like 2, 3, maybe 600 barrels a day on the high end with a lot of gas.
Higher GOR type wells,
And then if you have a gas well, you're going to be looking at something like a Ross and Gray correlation. So
I see a lot of people trying to utilize Beggs and Brill for gas wells.
Yeah, I think I want to say that one was really more for pipelines, and so it doesn't tend to match up. I haven't seen it match up anywhere, to be honest.
Okay. So, I know maybe in like your dry gas, like Marcellus, where their liquid yields are super low. I've seen that one used, but I agree with you. Like typically when I use Beggs and Brill, I'm using it on the flow line side.
I wouldn't think it would be a good one in Permian Basin or Eagle Ford.
I agree with you. I think like your Duns and Ross, Hagedorn and Brown. Another one that I found that tends to work pretty well with your larger flow areas, like over 2 7/8, or more of your non-concentric flow areas, kind of like annular flow, that Ansari typically does pretty good. Ansari, in my opinion, if you compare to like Hagedorn and Brown, is a little more conservative.
Exactly.
That VLP curve is a little heavier. So it makes for probably more accurate prediction of that flowing bottom hole pressure.
It almost always predicts a higher flowing bottom hole pressure. And you can run, if you've got SNAP or something like that, you can run all these against each other and see which kind of matches up with what you think is going on. Or you can use it like a weather forecaster would, where they, wherever you see the like hurricane paths, and they've got a whole bunch of models showing almost like a tree of different directions that can
spaghetti string.
Yeah, if you plot all these out, that's how it'll look. So you really have to have some technical knowledge in terms of, or at least run some flowing pressure temperature surveys and get a match so that you know which model is good for your liquid and gas mixture.
Yeah, you're right. And we'll talk about that later on in the presentation, that we do want to have some kind of data set to help correlate back to these multi-phase flow correlations. And one other thing that I like to mention too, just like that IPR curve, how that IPR curve changes over time, we find in a lot of these unconventionals that are multi-phase gradient change or correlation, changes over time, that we might flow initially under like a Hagedorn and Brown, and after we've recovered that frac load, our water fractions have decreased, our formation gas or GOR has increased, that well tends to transition into more of like a Duns and Ross flow correlation.
Duns and Ross tends to match in the later life stuff,
Mm-hmm.
and it actually has slippage in the calculation, whereas Hagedorn and Brown doesn't.
Yeah. So yeah, like Robert mentioned, it's important that when you pick your flow correlation, that we're picking that based off of some kind of data set. If it's a calculated or a flow and bottom hole pressure that we got from a memory gauge or downhole gauge or ESP, something to help pick those.
So what was on the previous slide?
Yeah, so we'll go back, but while we were talking about that, just want to touch on that.
Right.
So just kind of a general overview of that outflow performance, right? And so what we're trying to do is we're trying to match these VLP curves, we'll stick with one terminology, with our deliverability or our IPR curve. And based off of that intersection, we can then, of course, see what our flow and bottom hole pressure is and what our correlated production.
Yeah.
And it can also be helpful for like a guy like this one here, when it's not intersecting, what does that tell us, right?
Well, and as I explained it to someone the other day, that dark green curve, your IPR curve, is what the well is actually capable of.
Mm-hmm.
And then the more sort of left to right VLP curves are what your well can actually produce at. So the point where those two meet is where your well is going to produce, ideally.
Yeah. And we'll have a good example here in a little bit, is that, the nice thing about these IPR curves is they are non-dimensional, so that you can, if you can reduce your flow and bottom hole pressure, achieve a delta P of like 50% of a reservoir, you typically can achieve 70 or 80% of overall production. So what that means is a lot of times we don't necessarily need to play down here, that we can play up here, and the difference in production is typically pretty minimal.
Yeah.
Yeah. So yeah, good point.
Which is why you don't see ESPs on later life stuff. Usually they transition it to something.
Yeah, exactly. Because you don't need those massive drawdowns at that point. Yeah, good point. So yeah, let's kind of keep going through that, and really the bulk of the presentation, right? What we really want to talk about is how we can use this for production optimization, and then run through a couple examples. So, a big one I always get asked is, what size tubing should we put in there? Either for like initial production, or more importantly, later life, when maybe we have oversized tubing in the well, but the production's way down. So that's a big one for your VLP.
That's probably the most common request we get. Nodal analysis stuff.
I see that one quite a bit. You're right. And this one, when you look at those flow correlations, your flow area has such a big effect on that flow and bottom hole pressure, either positive or negative, that it's really important to size that, either if you're trying to achieve like an IP through it, or probably, in my opinion, more importantly, like that long-term life of the well, assuming your tubing's not going to fail.
And just like a pizza, small changes in air and radius are going to have a big effect on your flow area.
Yeah. So. Yeah. I like your pizza reference on that.
Yeah.
Pretty good. One of the things that we talk about tubing size, of course, life of well. If we plan to keep this well in some kind of dynamic form of artificial lift, understanding that tubing size, not just early on, but extending that through the life of the well. So hopefully we don't have to make a tubing size change later on in the well's life. Of course, if we're looking at gas lift, we can use that production optimization to understand injection gas rates. Is too much gas going to cause some frictional pressure loss and hinder production, or are we not injecting enough and still have some capability to get more production out? I see this one being really important, Robert, with operators that have centralized compression, because they can start playing that allocation game of which volume of gas do we send to which well to get the best production.
Yeah, and I've made it a standard. I send out a gas lift performance curve, which is basically injection rate versus flow rate.
And we'll show those guys.
Yeah, we'll show those on every nodal that we do. So.
Yeah, good point. Another one that, if you're playing in the gas world or the higher GOR wells, understand velocity gradients. Especially, I like to look at this for casing flow wells, when to kind of predict we're going to start seeing some of that liquid loading. And these velocity gradients can be helpful for that.
Yeah, those can be tricky though, because they're only applicable once you reach mist flow.
Mhm.
So if the well is slugging still, or it's not quite to that annular, flow regime, it's not really going to tell you the truth. It's just going to tell you, what your velocity
What's your
is.
flow velocity? Yeah, you've got a good point. Is that you got to make sure you're right in the right flow regime for that to
Yeah.
work.
That's the only time that your like Turner and Coleman critical loading rates actually matter, is once you reach that flow regime.
Yeah.
Before that,
If you're in
it's
bubble
not
flow
applicable.
or something
Yeah.
like that, it doesn't really matter.
Yeah.
Correct. Yeah. And then another big one too is the wellhead pressure, right? Because what you'll find is your correlation between wellhead pressure and flow and bottom hole pressure, it's not linear. It's usually like a 2 to 4 times multiplier, that if I increase my wellhead or decrease my wellhead pressure by like 1 PSI, it's usually like 2 or 4 PSI once we get to the bottom of the well. So picking that and sizing facilities, things like that. Again, more so in later life of the well, because this one actually becomes your best artificial lift when you get into some of these aged horizontal wells, is that you can reduce your wellhead pressure. You can gain a lower flow and bottom hole pressure greater than any other type of artificial lift,
Yeah.
even if the thing is on artificial lift.
Yeah.
So
It's an exponential effect. Like if you're looking at your flowing gradients, they're always like an exponential curve. So any change that you can make to the top is going to have an exponential effect on bottom.
yeah, you're exactly right. And then, of course, the big one in places like Permian and Delaware, where they're high producers, is should we go annular flow or tubing flow with a well? What's going to get us the best production initially? And then how long can we expect to keep that production before we make a change? Yeah. So good stuff. And we'll show you guys examples of all these kind of as we move through it, right? And so again, kind of looking at some of these examples is like our total gas to liquid ratio, that GLR, if it's on gas lift, injection gas plus formation gas, of course, wellhead pressure, flow area, all those things are really important when we're looking at these outflow curves. So we'll go to that and kind of show. So easy one to look at, especially when we're talking about artificial lift as gas lift, is how do we manipulate our GOR or GLR, and how does that affect ultimately our flow and bottom hole pressure? And so, of course, we look at this example. We have a range of 500 to 10,000, right? And of course, 500 yields the highest flow and bottom hole pressure. And in this scale, we have depth versus pressure. But we see that as we increase our GLR or GOR, we reduce our flow and bottom hole pressure.
Yeah.
We're getting that through that density reduction, that better mixture velocity. But then we also find that, hey, once we get past about, 2,500, we start to get less and less from a density reduction standpoint. And then actually, once we hit about 10,000, we tend to see a reversal.
Yeah. And you can tell a lot from these curves. So for gas lift, this would be a good example of it. If you were injecting on bottom, this is what your multi-phase flowing gradients would look like. But another thing, like I said, these curves are exponential. So if you look at that, you can see changing your wellhead pressure will have a much higher effect in the early life of the well when you have that lower GOR or lower GLR. That wellhead pressure is going to matter a lot more in the early life than it is in the late life. And then adding gas only does so much up to a point.
Yeah, because you can only reduce the density of the fluid by so much. And since the gas has a density as well, ultimately your best reduction in density is just simply going to be a wet gas gradient.
Yeah.
Assuming that you're not maxing out your flow capacity of your tubing size. And that's when you start to see that reversal right there. And I think this next slide kind of illustrates that, right? Is now we've taken that IPR, that inflow deliverability, and we've matched it against potential VLP curves based off of injection gas rate.
Yeah. And what you're seeing is, as it says in the title, is increasing gas rate. And if you notice, once we get up to like 2, 3, 5,000 injection rate, Not in the early life, it still gives you production gain,
Right.
but in the late life,
Yeah, they all kind of overlay on top
Yeah.
of each other. Yep.
so
And what we have here is we actually have two deliverability curves, one maybe current production, and then one predicted future production or deliverability of the well. And you can see that with this one, our reduction in reservoir pressure is what caused that. But you can see that, hey, if we inject here versus or this volume versus this volume, we get a significant increase in both production as well as reduction in flow and bottom hole pressure. But as that well ages out, we can say maybe we can reduce injection gas or, injecting at the highest volume is going to yield the same production as the lower volume, just because we've essentially maxed out that density reduction. We just simply can't reduce the density of those fluids anymore.
and realistically, as we said, that IPR curve is not just going to reduce in reservoir pressure. The slope of it will actually change too.
Yep.
Yeah. So in the later life, you really want to focus more on just reaching that critical rate. And in the early life, give it as much injection gas as you can.
Yeah, density reduction without overcoming that capacity based off of your flow area. And I think our next slide kind of illustrates that, right? And so what we're seeing here is just a gas lift performance curve. And for it, what it's looking at is our production over here on our X and injection gas volumes on our Y-axis. And so you can see that to a point, as we increase our injection volumes, we're getting pretty good yields and production, right? But eventually we tend to just max out that volume capacity of our flow area. And then after a point, we tend to just flatline and actually start to see a reversal in that production.
And this is a later life well. You're seeing like 200-300 barrels on that Y-axis, and then I think it's 2 7/8 inch tubing, right?
Yeah.
Or is this?
And so that's a good point, Robert, is like your flow area is going to have a compounding effect on that too. Is if we made this a smaller tubing, we'd probably see a quicker reversal. But if we had this as like annular flow, it tends to just constantly increase because our flow area, our handling capacity is just so large.
Yeah, and you can see, like, even as you start to over inject, it doesn't have a massive effect on your production, unless you want to get the talks about port sizes and moving up valves.
Right.
We'll leave that.
Save that for
another
discussion. Yeah. But this one's good. I prefer this one, especially when we're looking at multi-well compression or centralized compression, because then you can build these curves based off of water cut, total production of the well, and ideally send your peak gas volume to your lower water cuts or your higher producers and scale back on your injection volumes for maybe your lower producers or your higher water cut wells. Yep. Basically allocate that gas to give you the best economics from how much oil can we get out of the ground based off of how many units of gas we send back to it. So this one, you can use it for individual well. I really like it when we start looking at like multi-well.
And so for this case, I think your ideal injection would be around 400 or 500 probably.
Yeah, right in there. Yeah, good point. So another thing we talked about, again, water cut. I like to show this one. In reality, most areas we don't tend to see a dramatic change in water cut, but again, it's all based off of that frictional pressure loss of our flow area as well as our density reduction. And so as we increase our water cut, of course, our density of that multi-phase flow increases and our frictional factors tend to increase as well. And so, when you're looking at higher water cuts, maybe you tend to plan for maybe a larger flow area to help reduce some of those frictional pressure losses that cause an increase in your flow and bottom hole pressure. But you can see, of course, as we increase or decrease our water cut, even if we keep our production rates fixed, our flow and bottom hole pressure is going to change.
Yeah.
So a big one that I know you probably look at quite a bit, and I do as well, is flowing wellhead pressure. And so here's an example of a fixed tubing size, a fixed production rate, a fixed end of tubing, but we're just simply changing our wellhead pressures, right? And we go from a really low wellhead pressure to about 600 PSI or so on the high end. And you can see, like you mentioned earlier, Robert, that if we increase our wellhead pressure by 200 PSI, That's almost a 400 psi
Dang.
downhole, right?
Exactly.
And so if we can just simply reduce our wellhead pressure, we can get some significant gains in flowing bottom hole pressure, just simply by controlling wellhead pressure.
Yeah.
No artificial lift, no injection gas changes, no tubing size changes, just controlling that wellhead pressure. And so, from an operation standpoint, Robert, a lot of times we'll see if it's casing flow, we flow out of two sides or two outlets on the flow block. Or maybe if we have 2 7/8 tubing in the well, we run a 3.5-inch flow line, things like that to help reduce that surface pressure as best as we can.
And taking the bends out of the tubing.
That's a big one. Yep.
Making sure your flow line's as straight as possible.
Yes, sir. Yeah. Because any kind of directional change, especially 90-degree directional changes, really hinders that. An old saying I remember was 990s equals a bull plug. So if you have 990s in your wellhead, you might as well just close the well.
Right? You might as well think of each one as like putting a little choke in there, a little pressure drop, essentially.
And I don't think I've ever seen 9 on a well, but I have encountered 5 or 6 directional changes from the wellhead to the separator. And so you think about how those little chokes end up backing up to your wellhead pressure.
And this, if you can reduce wellhead pressure for a gas lift well, that has a big impact on where the gas is expanding, right? And it'll make your gas have a larger impact, essentially.
Because it expands essentially deeper downhole, right?
Yes.
Because you have less pressure at any given depth in the well that's going to try to constrict or compress that.
So that's why we keep harping on this, is because as gas lift people, we want to see that really low wellhead pressure, because that's going to make the gas lift look better.
Exactly. Yeah. Yep. Good point. And another thing too is, I'll use like Barnett Shale, for example, and this of course is other areas too. But one of the things that we'll see is well site compression, wellhead compression, where we're actually using the compressor to pull the wellhead pressure down. And so when we start getting into later life wells, we can pull wellhead pressure down to say maybe 75 or 50 psi. And again, just trying to gain every little bit of flowing bottom hole pressure we can out of the well. So yeah, that's a big one. And yeah, I apologize. We'll talk about that one quite a bit because it is really important. Yeah. And here again, here's another representation of that, right? So this is that VLP curve independent of the deliverability. This is what it actually looks like when we match that change in wellhead pressure against the deliverability of our well. And of course, you can see this is going to be our highest wellhead pressure, and this is going to be our lowest wellhead pressure. And I mean, that's significant, right? That's 30-40% of your drawdown.
And even the smaller ones, and even the smaller wellhead pressures, you can see there's a big difference between 150 and 50 and 100. That's 50 barrels, that could be
just through a simple wellhead pressure,
just for a 50 psi change.
So this is when it really becomes important, because this one is actually matching what our wellhead pressure versus our deliverability is.
And this I base this model off of a real late life well. So it's you can imagine if you're looking at early life, it's just going to be that much more of an impact.
Yeah, exactly. So yeah, big one. This is it really important to look at. And you can use this for a casing flow well. Or you can use this for really any kind of artificial lift. Yeah, because any artificial lift typically is going to benefit from a lower wellhead pressure. There's some ESP and some sucker rod guys that might say you might get some more gas breakout in the pump and things like that.
Yeah.
But ultimately, any kind of reduction in wellhead pressures for any form of artificial lift, and even a naturally flowing well, is always beneficial. So I think we've beaten that dead horse pretty good.
Yeah.
But and I'll tell you too, Robert, over the course of 18 or 20 years in the artificial lift industry, this one has become more and more focused on in the basins, whereas it used to be like wellhead pressure is wellhead pressure, but operators have gotten a lot better at trying to reduce those things. So let's talk about another one that's really important. We'll talk about flow area, right? And I'll look at it from just a tubular standpoint, and then also how we can change that flow area from things like annular flow. And so this is the big one too, right? Is our flow area is probably what do you think? Maybe our biggest factor when it comes to those multi-phase flow correlations. And so if you increase or decrease your flow area, you can change your flow and bottom hole pressure. And here we have a couple VLP curves from 2 3/8 to 2 7/8, 3.5, and I guess heavy wall 4.5 inch tubing. But you can see that as we increase that flow area, we can reduce that flow and bottom hole pressure.
Yeah.
One thing I like to note about this is it does have to match your production, meaning that we don't want to set big tubing for a low production rate. So when we're looking at these flow areas, these tubular sizes, we want to match them to production, meaning that if we're going to produce 100 barrels a day, we probably don't want to put 3.5 inch tubing in, right?
Yeah.
But if we're going to produce 3,000 barrels a day, we probably don't want to put,
yeah, you're going to need it.
So you need to size your tubing to your expected production. And I think this next slide hopefully illustrates that, right? Is that actually next couple slides, but we look at our different VLP curves for different tubing sizes and we match those up to the production rate. And so here we can see that maybe this tubing is a little too small for that production rate, but then these two sizes tend to overlap with each other.
I think this one was meant more to show sort of in a late life scenario with a lot of gas. Looking at a Duns and Ronson curve, the larger tubing isn't going to give you a benefit here. Essentially, they cross over.
Yeah,
so I think the base case is 2 7/8, and the larger one might be 3.5 inch. So
exactly, and so you can see in this case, our volumes don't meet that flow rate or flow capacity, right? So then it doesn't make sense to upsize that flow area. And I'll jump ahead a couple slides to kind of illustrate another version of this. So again, we're changing our flow area, we're increasing or decreasing it, but instead of just making our tubing bigger, we're changing our flow path. And a little history behind this is why we're doing this is typically we're constricted by our casing size, right? Like what's typical casing size that we see in these resource plays?
Usually 5.5.
Yeah. So
probably the most common.
We can't really put more than like 2 7/8 tubing inside. Maybe we can do 3.5, but fishing superintendent's probably going to be pretty mad at us if we do that. So, you look at it from this standpoint, right, is now we're starting to have a substantial difference in production rates just by changing that donut, that flow area size. We've got a lot of food references in this one, don't we? And so like with this one, it would make sense at this point of the well's life to maybe go to that annular flow, right? But what you illustrated back here is some later life deliverability curves, and that benefit starts to kind of peter out.
Yeah.
And it's just because we don't have the volumes to fill that pipeline, fill that tubing capacity, that flow area capacity. So maybe we say annular flow makes sense up here, but we need to start considering conversion to tubing flow at these later lives of the well.
Yeah, and then you also got to start considering your critical rate in the later life. So going down to that smaller tubing is going to keep it's going to allow you to conserve gas if you're injecting gas.
Yep, that's a good point.
And it's going to make sure that you're hitting your critical rate so that the well's not loading up. So.
Yeah, so it's going to help with that stability because we might start seeing just big changes in our flowing wellhead pressure because the well's just flowing in these really erratic slug flow pattern. Yeah. And what we try to do is we kind of summarize some of your capacity here. Now, again, I'm sure people are going to say they've produced definitely a lot more up these tubing sizes, but this tends to be like our happy area, right? Yeah. If you have the horsepower, reservoir pressure, then you can definitely produce rates substantially higher than this, but this tends to be like where everything is in that stable, like transition flow or annular mist flow regime.
Yeah, you talk about horsepower. I've seen offshore wells that could produce up 3.5 inch at 50,000 barrels a day. So like it's all relative to your reservoir. But ideally, like you want to get a larger tubing size. If like this is a good range to make sure that you're not frictionally limiting your well.
Yep, and that's a good point. Is like that, and then you're maintaining a stable flow regime too, without compensating for maybe over injecting on the gas. Because like I'll use example here, like we can produce well below 1,000 barrels a day in 3.5. If it's on gas lift, we have to constantly increase our injection gas to basically fill that void that our production is.
You're going to be injecting like 1.5, 2 million to try to fill that tubing up.
Whereas if we just downsize to that point to say 2 7/8, we can probably cut that injection volume by like half, and still be in that stable flow regime. So yeah, good points on that. This is a big one. I really like looking at this type curve, tubular versus annular, especially when you're transitioning from casing flow. If you have the biggest flow area, casing, and then now we're trying to pick our tubing, this becomes really important because we've seen this where, hey, we have casing flow and we put tubing in and they get this like iconic like stair step drop in production and want to know why.
Yeah.
Well, there's your reason. It's all
so that's the next thing. We put a hybrid design in where we have gas lift valves for both annular and tubing flow, and we get constant requests. Okay, well, should we switch it now?
Yeah,
it's like no, wait,
go and
wait
update.
Wait till you get down to like 800 to 1,000 barrels, and
Yeah.
then you can swap over because you can see, as we talked about, where it meets that IPR curve is where it's going to produce, and in the later life there, you can see on the x-axis there's very little difference. So that's probably where you'd want to swap over.
Yeah, that's a good point. So this is outside of gas injection. I really like that production optimization software from your flow areas, because your flow area is one of your biggest factors that affect those VLP curves. So, and one last thing, we talked about this early on, Robert, is matching that data correctly. And so a couple different ways to pick your multi-phase flow correlations. You could take a dart and throw it at it, and whichever one the dart hits, you could go with that. You could use reference from offset wells or operating areas, or you could collect data such as flowing bottom hole pressure, either typically through like a memory gauge or a live downhole gauge. And
in this case, we have flowing PT survey. So this is the most fun. This is like what I was talking about earlier, where you have the
spaghetti
weather forecast with all the spaghetti lines for where the hurricane's going to go. This is the same sort of thing, and you can see we've got 5 or 6 different models on here, and only one of them fits our flowing PT survey.
Yeah, so we know this is the preferred multi-phase flow correlation for this data. And we have another one over here that you can see now we've predicted a higher flowing bottom hole pressure or production gradient and a lower production gradient. We find that, I think this one's Hagedorn and Brown, tends to match up quite well with that data survey.
Just to make it clear, the little crosses on there are your flowing PT survey.
Yeah, so that's the actual pressure data that we collected in the well.
Yeah.
Yeah. And so you can do this with a survey like Robert shows here. You can try to predict it with a single data point. What you tend to lose with a single data point is some of these pressure changes up above that, but you can use that information. But it is important to ask around to see if you can collect that data to match these up. And personally, if we see like a big water cut change over the well's life, or like a GOR change over the well's life, it's good to go back and update those multi-phase flow correlations.
And it depends how much you're relying on these models, right? Of course, but you can run this. You don't have to run it on every well. You just run it on one well that you know is representative of a lot of your other wells, and that way you know which model to use for going forward.
Yeah, yeah, you're exactly right. Is that you don't need to do this on every well.
Yeah,
pick one, use that as your example, and unless you start seeing the results of this production optimization change, that's when you should probably go back and recollect that data. Yeah, good point. So a couple other things just kind of summarize, right, is you can use this for any type of well evaluation, picking tubing sizes, expected production rates, artificial lift, if we have it on gas lift, how much to inject. So you can use it for a multitude of any kind of outflow performance. Of course, you can use it for inflow too, but we primarily wanted to talk about it from outflows.
And we didn't even talk about depth of injection.
Mhm.
And, you can also look at, where you should set your tubing. Should we set the packer a little bit deeper? How's that going to affect your
Yeah.
production? All those things
Go into it.
Yeah.
Yeah, you're exactly right. And so, one of the big things that you've brought up a couple times is like calibrate that data to well tests and flow and bottom hole pressures, things like that, both for the inflow and the outflow side. Of course, we'll mention it one more time, minimizing that wellhead pressure throughout the life of the well, both early on and later life, tends to have a big effect on that.
Yeah. And in early life, people really preach choke management and like not letting the well off too quickly. But frankly, like if you're opening the choke up all the way at the beginning and the well's dying early, that just tells you need to put artificial lift in
sooner. Yeah, that makes a good point. Yeah. And then really pairing that inflow and outflow together to understand your expectations of the well. That's a big one that I see often too, is that an operator puts a well on artificial lift and then calls and says, why aren't we making 4,000 barrels of fluid a day? Well, we go back and look at delivery curve, and even at the absolute flow, they can't make 4,000 barrels a day. So, understanding that relationship, and then, being able to expect, if you put this well on any type of artificial lift, what's the max flow you should be able to get out of it? And if that's ESP or jet pump or gas lift, should be able to use that.
And if the well's going strong at the start and you're trying to put gas lift off the bat, and you're seeing a drop in production going from casing, that tells you you're putting it in too early.
Yeah, and that friction's taken over at that point. Right? Yeah, and that's the other thing that we didn't talk about, is that friction is relatively easy to calculate in these things, to understand how much that's going to have effect on it. Yeah, good point. With that, just one other thing to update you guys on. Again, thanks for joining. We'll switch to Q&A here in a little bit, but touch on some of the upcoming series trainings that we have. We'll plunger lift. We'll dive into some capillary tube and downhole gauge usage, and then kind of wrap up the year with some more advanced plunger lift optimization as our 102 series, and then also plunger assisted gas lift. How can you use that to reduce injection rates, increase production, cut back on scale and paraffin and things like that? So with that, Robert, thanks for joining, and let's switch over to Q&A.
Fun being in front of the camera today.
Yeah. I'm glad you could join us. So I'll stop sharing this. We'll switch to Q&A, and we'll wrap it up for you guys. Yeah, perfect. So one of the things that I saw, Robert, is from the question is, when we're wanting to build a deliverability case for the well, what kind of information, like what are the few things that we have to be able to build that inflow and outflow relationship?
The big one that operators don't tend to have is usually your reservoir pressure.
Okay.
That can definitely have a big impact on, especially what you're seeing at the top of the curve with your PI. So like, if you don't get your reservoir pressure right off the bat, then your differences, I guess, between, like, if you're modeling tubing, for example, and you want to know 2 7/8 versus 2 3/8, the 2 7/8 is going to show a lot more production gain than so if you had too low of a reservoir pressure, that's going to be a higher PI. And that would make the 2 7/8 look a lot better than it should, essentially. Whereas if you have a too high of a reservoir pressure, well, you're going to have almost a vertical line, and a really low PI, and it might show you can use 2 3/8 at 2,000 barrels.
So you might underestimate your tubing size on that. Yeah, that's a good point. So reservoir pressure, or a way to estimate reservoir pressure, is important.
Yeah, the IPR and VLP curves, they're really a great way to visualize how any change to your well or your change to your reservoir is going to impact your production. So
I guess if you are unsure on reservoir pressure and can't shut the well in, you could probably do a min and max within a expected range of reservoir pressures.
Yeah.
And that way you could just at least see
we do that all the time. That can be your P90 or your P10 case for the well.
Yeah, that's a good point. Perfect. Yeah, and another thing that I see a lot too is how long can you flow a certain tubing size? And so is that something you can glean from this as well? Like
Yeah.
how long will 3.5 tubing be useful before we need to switch?
Yeah, and that's where those graphs that we showed come in, where you have, multiple IPR curves plotted on the same hydraulic correlations, because your hydraulic correlations aren't changing over
Mhm.
time for the most part, unless your water cut's changing.
Yeah.
There are some things that affect your hydraulic curve, but for the most part, you can kind of figure out where you need to swap over, just modeling this stuff out in
Okay.
advance. Yeah.
Perfect. Well, Robert, thanks for joining us this week, and glad you got in front of the camera. And good luck on your wedding this weekend.
Thank you.
You bet. And guys, thanks for joining. And we'll have this out on website for anybody that missed it. And then, of course, we'll have Plunger Lift 101 next month. So everybody, thanks for joining and have a good week.
Thank you, guys.
Yep. Thanks, Robert.